And Graham, please take it away. The floor is all yours.
Okay, so I hope that you can see what I'm sharing from my screen.
Yep, we can see it. Yeah, no problem.
Okay, so the background to this talk is just observation about certain things that people have said about, or certain claims that people have made about epistemic consequences of Gödel's incompleteness theorem. In particular, recently I read a paper by Dennis Turner, so that's him in the photograph, a theologian, and he compares our knowledge of mathematics with our knowledge of God on the kind of Thomistic way of thinking about God. So the idea is no matter how you ramped up our finite capacities, you would get no closer to having a full grasp of the nature of God. It's just not something that we can achieve with the kinds of capacities we've got. And his thought is that we learn from Gödel's theorem something like that. No matter how you ramped up our capacities, there would be truths of mathematics that we would never get to. There are truths of mathematics that are forever beyond our grasp. And there are other people who've claimed epistemic consequences for Gödel's incompleteness theorem. There are a whole lot of theorists, people like Derrida, Deleuze, Lacan, I won't read out my list, who make very big claims about indeterminacy and undecidability of theories that they suppose you get out of Gödel. And if you're prepared to wander onto the internet and consult with the folk, you get things like this my third example from Callaway. It's impossible to reason a way to a conclusion common to everyone on any subject matter. We must always choose according to our faith. Now, I'm particularly interested in Turner. I'm not at all interested in what the people on the internet say. I just included that for completeness. There are other kinds of unusual or sort of big claims that people have made for the incompleteness theorem. So I guess kind of notoriously, there are people who claim that there are metaphysical consequences of the incompleteness theorem, people like Roger Penrose and before him, John Lucas. I'm not going to be talking about that today, though it's possible that some of the things that I've got to say might have some consequences for their claims as well. This is not going to be a technical talk. I'm not a logician and things might go badly wrong, but that's okay because there are plenty of logicians in the audience and you'll be able to fix things for me. So the first thing is, okay, so what am I talking about when I'm talking about Gödel's incompleteness theorem? Well, I'm going to take it that this is a statement of the theorem. Any consistent recursive axiomatization of arithmetic is incomplete. There's a bunch of terms there that need explaining, so I'll now explain them just in case there's anyone in the audience who isn't familiar with the incompleteness theorem. So first word, consistent. The understanding here is based in classical logic. There's a bunch of different ways that you can say what consistency and inconsistency are in classical logic that come apart when you move to logics other than the classical. It will do, I think, for my purposes, to think of it like this, that a consistent theory doesn't contain every sentence. Something like that will do for consistency. Axiomatization. So suppose you've got a theory. I'm thinking of a theory as a bunch of claims closed under logical consequence. If you imagine throwing some things out from your theory, but when you reclose, you get the theory back again and you don't get more, then you've got an axiomatization for the theory. Of course, axiomatization in general is not very interesting. Generally, if people are looking for axiomatizations, they're looking for minimal axiomatizations and they're looking for ones where the, in consequence, where the axioms are independent, sort of logically independent of one another. Okay, so now consistent recursive axiomatization. Well, recursive, I don't need consistent, but I need axiomatization perhaps to explain this. So recursive axiomatization is going to be one for which you can perform. So if we've got what really is a recursive axiomatization of a theory, then for any sentence that we can form in the language of the theory, we can make a mechanical check to see whether or not it's one of the axioms. Okay, if our axiomatization is finite, this is really easy. We take our sentence and we just run it down past all of the members of the axiomatization and check to see whether it's in there. It needn't be that a recursive axiomatization is finite, but the idea is still the same. You've got a way of checking whether or not for any sentence of the language it is or is not an axiom. Maybe I should have started with arithmetic. Anyway, arithmetic here is going to I'm not going to be very careful about what arithmetic is. Think of it as the theory of the natural numbers, 0, 1, 2, 3, 4, equipped with a couple of operations, maybe addition and multiplication. We don't have to go that far. We could have weaker arithmetics where we do away with one or other of those operations. One of the things about the Godel result is that you don't need very much. Your arithmetic doesn't have to be very strong. There are much, and I will talk about a particular example later. Okay, so any consistent recursive axiomatization of arithmetic is incomplete. The only thing left to explain is incompleteness, which I'm going to understand this way. So for any consistent recursive axiomatization of arithmetic, there's at least one claim A in the language of arithmetic for which neither A nor not A is a theorem, given that we're proceeding classically, one of A and not A is going to be true. So it's going to be a consequence of this that there are truths in the language of arithmetic that don't follow from our axiomatization. So here's a very first thing that I want to say, very kind of quick and dirty thought. Gödel's incompleteness theorem is about limits on axiomatization. And it's very hard to see what connection there could be between limits on axiomatization and limits on knowledge. And that's true even in mathematics. So back in, what was it, 1903, around about then, near the beginning of the 20th century, in the Principles of Mathematics, Bertrand Russell, that's him there in the picture, observed, I think correctly, that we judge the fitness of axiomatizations of mathematical theories by their ability to deliver as theorems results that we take independently to be true. So I think this is a kind of pre-Gödel thought. It was already recognized that it's a fiction to think that mathematical knowledge rests on knowledge of the truth of axioms. And once you've recognized that point, it seems rather weird to think that somehow or other, because there are constraints on what we can do with axiomatization, that's going to generate constraints on what we can know. So I said to Guillermo before we started that I would pause at various points and see if people had questions. So this is one point where I want to pause. So if there's anything that anybody would like to raise at this point, raise your hand and off we go. It doesn't look like there's anything, so maybe I'll continue.
Sorry, I had a,
yeah,
Paul,
no, go.
Paul has a question.
Okay, so
Yeah,
Paul can go first.
just very quickly, Russell in 1903 provocatively called this inductive justification of the axioms. And Whitehead and Russell in the second edition of Principia picked up that language again.
Yeah. So
this is something Russell, I think, didn't change his mind about.
So James, you wanted to say something?
Yeah, I mean, like, I get a little bit of personal bias of my interest in philosophy of maths coming through here. I'm interested, so if we're gonna like the usual alternative Or I guess, do you have much of an opinion on the alternative in the case of, like, say, mathematics or knowledge in general of what's going to be its justification basis? Because usually the reason to appeal to maximization is like there's an idea that we want this to underpin, and it was predominantly done in response to the like crisis of foundations of mathematics. Like, do you have a particular stance on what is going to underpin mathematics if it's not going to be the maximization, right? Like if we're reverse engineering axioms, then we have an independent sense of truth that needs to be underpinned by something.
Yeah, so I don't think I have a good answer to this question, right? No, I don't have a developed philosophy of mathematics, but it does seem as though working mathematicians are quite happy to start proving stuff before they've got a set of axioms, right? And so there's got to be some story to tell, even if I don't know what it is. Okay, so let's go on. So that was just the kind of first step. So to do the next bit, I need a particular account of arithmetic. So I'm going to say a little bit about Peano arithmetic. So Peano provided axioms for arithmetic. It wasn't his work alone, Dedekind and various other people working on axiomatization of arithmetic at the same time. And it's a very popular choice for people who are working in metamathematics. Slightly technical point. Peano's original axiomatization was second order, but I want to consider a first order axiomatization. And in order to have a kind of recursive first order axiomatization of Peano arithmetic, you need infinitely many axioms. The way you get them is by having an axiom schema, and that kind of explains where the recursivity comes from. So here's a statement of either part or all, depending on your point of view, of the axioms of Peano arithmetic. 0 is a number, the successor of any number is a number, every number has a successor, 0 is not the successor of any number, and mathematical induction, all the instances of mathematical induction. Peano had some axioms about identity, which we now think of as part of the logic. Maybe you want to throw in some axioms about multiplication and addition, or maybe you think that we're just going to define those up and we don't need axioms for them. To keep the discussion simple, I'm going to take it that this is the kind of axiomatization of Peano arithmetic. It's pretty standard. Now, what I want to point out is that there are serious inescapable limits on our access to the theorems of Peano arithmetic. This is something that I assume that people like Dennis Turner haven't thought about. I'm going to labour this point probably at greater length than it deserves, but it seems worth making this point. So we have finite working memory, we have finite processing speed, we have finite lives. I'm going to sum that up by saying just that we're kind of cognitively finite. And I'm going to illustrate these limitations by thinking about a simple task, which I'll get to on the next slide, involving some of the theorems, a selection from the theorems of Peano arithmetic. What I want to suggest is that no matter how you bump up our finite cognitive powers, there are going to be truths of Peano arithmetic that remain beyond our reach. But there's no way to get from there to there are truths of Peano arithmetic that no matter how you bump up our finite cognitive powers remain beyond our reach. And one way of thinking about what Turner is doing is that maybe he's kind of illicitly making a jump of this kind. Okay, so God's arithmetic exam. So God's going to set us a series of arithmetic exams that use n-digit to some n sums. The way it's going to work is this. He's going to give us all of the true, say, 1-digit sums, 2-digit sums, 3-digit sums. And then he's going to give us 100 near miss ones where 1 digit is out by 1. And I'm going to count not having an initial 1 in the n+1th case as a kind of near miss, because that's one way. And I'm going to think that we're only looking at these sums either with the same number of digits in the bottom line as in the top two, or with an additional 1 at the beginning. All right, so think about the 1-digit sums. We have things like 2 and 3 are 6 and 2 and 3 are 5. The first one I gave, you need to write dozen equals in order to get a theorem of Peano arithmetic. The second one you need to write in equals in order to get a theorem of piano arithmetic. We are going to imagine an exam with 200 questions on it, right? Because there were 100 of these one-digit sums with a correct answer, because you can have any of 10 digits, right? And then a bunch of near miss ones. So an exam with 200 questions on it. I don't know how long it will take you to do this exam. It'll be not too taxing. It might take you 3 or 4 minutes, right? And if you were really keen, you could actually set to and examine every single one of the relevant theorems, one-digit theorems, given the constraint that we're not going past having a 1 in the initial second digit if we need one. If we move up to 2 digits, right, roughly we're going to increase the size of our exam paper by 100, because we can write any of the 10 digits after any of the digit that we already had, right? Roughly, so a roughly 100-fold increase in the complexity of our exam. So in the 2-digit case, God's going to give you an exam paper with 20,000 questions on it. That's going to be more than tedious. It's going to take you a bit more than 100 times as long to do it. I don't know, maybe 15 or 16 hours. I wouldn't try to do it all at once. That would be just totally mind-numbing. But you could do it. You could, and in theory, you could acquaint yourself with all the consequences of the piano axioms of this form. Let's ramp it up a bit further. Let's go to 45 digits. So I've given you an example on the screen, a 45-digit sum. And I don't remember whether it's a theorem if you write in equals or if it's a theorem when you write in dozen equals. I don't remember. God's got a problem now, though, because if you think about the multiplying by 100 every time you go up by a digit, we've now got about 10 to the 90 questions on our exam paper, and there aren't that many elementary particles in the observable universe. So God's going to have serious difficulty setting you this exam, and you've got no hope of completing it, right, with your 10 years and the capacities that you've got. However, if you look at this single sum, you can work it out. It might take you a minute or two, but you'll be able to work out. It might take less, but you'll be able to work out whether it's a theorem or not. There is a question about whether, even if you can work out whether it's a theorem, you really have any grasp of what it's saying, right? That's a question that you might come back to, that there's no intuition that goes along with this, even once you've worked out whether or not it's a theorem. So whereas the 1 and 2 digit papers were in the green, so we could do everything. We're now in a kind of grey zone. There's some things we can do with these 45 digit sums. Even if you can't really know what it's saying, you can at least know that it's expressing a truth. Okay, so now let's really ramp it up. Let's think about, so 10 to the 100, a Google is a kind of large number. Let's think about 10 to the Google, a Googleplex. Right, now imagine these sums with a Googleplex digits. Right. Obviously, God couldn't give us the 45-digit exam. God can't give us the Googleplex exam either, but you can imagine a universe in which in front of you there's, let's make it fancy. So there's 3 strips of metal and the numbers are kind of pressed into the metal. And it goes off in that direction beyond the limits of the observable universe, and it goes off in that direction beyond the limits of the observable universe. And you've got your 10 years. Probably you're not going to find out if it's, supposing that it's an inequality, you're not going to discover the error that tells you that it's an inequality. If it's a theorem, you're never going to know. Right, the single question, right, what's expressed on this sheet of metal is something that's just completely inaccessible to you. Right, there's no sense in which you can grasp it. So I think there are serious limitations on our knowledge of the theorems of piano arithmetic. And it doesn't matter how we ramp up our powers, right? You can imagine being quicker and smarter and having much bigger working memory and being able to hold the 45-digit thing in your working memory and grasping it in the way that you can grasp a 2-digit sum. And you can imagine, though maybe it takes a lot more work, that you could have the capacities to grasp the googolplex digit sums. But wherever we set your capacities, you're going to be placed just as we are. There'll be this infinite domain of stuff, much more complicated, that you can form no conception of whatsoever, that you've got just no access to, right? So there are limitations on our knowledge of the theorems of piano arithmetic, and those limits are inescapable. No matter the level of our cognitive powers, there'll be theorems of piano arithmetic that just elude our grasp. Finally, although what's beyond our grasp here seems kind of boring and uninteresting, you might think that it's more mathematically interesting than what's allegedly shown to elude our grasp in the proof of Gödel's incompleteness theorem. As far as our epistemic limitations go, it's very hard to see why you're going to make a fuss about the Gödel theorem if you weren't already making a huge fuss about the fact that most, in some sense, most of the theorems of piano arithmetic are beyond our grasp. Right, you know, the ones that we can grasp are of measure 0 in the total set. Okay, so that was the second thing that I wanted to say. So I should pause at this point and see how people respond to this argument. Maybe, yes, because it says interim summary. Every time I get to a slide that says interim summary, that's meant to remind me that I want to stop.
Sorry to interrupt again, or to go again. I mean, just on this last idea that there are like these kind of limitations that you're talking about, like oh well, you know, even if they are ostensibly, one could eventually have the cognitive powers to reach them. Like the reality is, like there will be always more stuff beyond it.
Yeah.
And contrasting it with the Gödel sentence, like I think it's worth mentioning that like there are other, like the Gödel sentence was kind of the first prototype of undecidable results, but there are plenty of genuinely very mathematically interesting results.
I'm going to get to that, so you should stop.
Okay, yeah.
I am going to talk about that. That's later.
Sorry, Grant, may I say some small thing as well?
Yeah.
Real quick, just I mean, even if we just focus on the Gödel sentence, that as James said, this is really pretty much cooked up for the purposes of that theorem. In fact, what we can learn from the theorem is not so much that it's beyond our reach. It's just that we can never formalize the methods by which we can learn about it, because we know, for example, that the Gödel sentence is true, right? Like this is epistemically something that we can reach a state of knowing. However, it's just that the methods by which we know it are not the sort of methods that you can formalize in a recursive manner and so on and so forth. At least not for every possible sentence that you could possibly want to know about, no, something like that. So just that very small remark.
Yeah, so I'm going to say more about that, I think, as we go on. If I haven't by the end, remind me, and I'll make some more comments. Okay, so now I just want to digress briefly and talk about something else, which in some sense may have some connection to Gödel's own discovery of the incompleteness theorem, because it's well known from his notebooks that he was thinking about the Löwenheim-Skerlam theorems in the year or so before he produced the incompleteness theorem. And you might think of, although I doubt that this is right, but you might think of what he did as finding a way of taking something that looked like it was a kind of meta result and pushing it down into the object language. So anyway, I want to think about epistemic limitations that you might think that we can learn about by thinking about Leeuwenhoek-Scullin theorems. So, okay, so that's the lesser Leeuwenhoek. A first order theory with a countable model has models with all higher cardinalities. That's the version that I'm going to go with. Since the standard model for piano arithmetic, I'm going to call it S, is countable, it follows that piano arithmetic has models with higher cardinalities. So suppose that T is such a model. Intuitively, and there's a reason why that's in italics, and there's going to be a bunch of other seams that are also in italics. That's to warn you that I don't really mean what I'm saying at this point. Intuitively, since S and T have domains of different cardinalities, there are arithmetical claims that have different truth values in S and T. Let A be one such claim. Clearly, neither A nor not A can be a theorem of piano arithmetic. So intuitively, we have arithmetical claims for which neither A nor not A is a theorem of piano arithmetic, and that should sound rather familiar, right, given what I said earlier. I will digress for a minute and just explain what a non-standard model for piano arithmetic might look like. So in my picture here, on the left-hand side, we have 0, 1, dot, dot. I'm imagining over there, just in that part of the diagram, is the standard model for the integers. All right. And then what's stacked on top of it, the bit that goes dot, dot, omega minus 1, omega, omega plus 1, dot, dot, is what you would have got if you wrote a copy of all of the integers, so positive and negative in there, replaced 0 with omega, and then appropriately replace the sort of minus 1, minus 2, minus 3 by omega minus 1, omega minus 2, omega minus 3, and so on, going up the other way. Now, that's still a countable model. To make an uncountable model, let's go to the real number line, which I've written here. Now, imagine turning it on its side so that 0 is at the bottom and 1 is at the top. Replace 0 over here with the standard model of the positive integers, the standard model for piano arithmetic. And then for every other number, R, replace it with a copy of what's above on the left-hand side, except that where you've got omega, replace that with R omega. So we're going to have dot, 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 R omega minus 1, R omega plus 1. And so, for example, at point 2 will be replaced by a copy of this whole thing with the 0.2 omega minus 1, 0.2 omega plus 1, and so on. That whole thing is now still a model of piano arithmetic. You can check that. 0 is there. Every number has a successor. Nothing's a successor of 0. Every number is a successor of something. And obviously there's some tinkering to make the inductive thing come out right, but we have now an uncountable model because there are uncountable many reals in the interval from 0 to 1. So that's what a kind of an uncountable model for piano arithmetic might look like. Okay, so that was just a digression for people who are a bit puzzled by that. The existence of non-standard models of first-order axiomatizations of arithmetic with different cardinalities seems to show that we can't get our first-order theories of arithmetic to tell us the cardinality of the domain of natural numbers. Let A be the claim that the cardinality of the domain is LF null, then it seems that neither A nor not A can be a theorem of first-order theories of arithmetic. I say seems. What I've developed here is a version of Scullom's paradox. I forgot to note on the previous slide, I had a picture of Scullom. It's fairly widely agreed that there's no genuine puzzle here. What the words we use in our first order sentences denote is one thing. What those words denote in particular models in first order logic is quite another. It's simply true that in the intended model, the domain is countable. But there are some philosophers who've taken Scullom's paradox to show that, for example, we never really know what we're talking about. I'm thinking of Putnam in particular, the Scullom's paradox paper back in the 70s. Were that so, it would be a way more dramatic epistemic consequence than anything that can plausibly be squeezed out of Godel's incompleteness theorem. And I think that it's true that there's a sense in which within the first order language of arithmetic, we can't rule out non-standard models, right? That's obvious, but we can straightforwardly talk about the standard model of arithmetic in an appropriate meta language. When we think about what epistemic limitations there might be here, we should adopt the perspective of an appropriate meta language. If we can't do that, we're just, you know, soaring off the branch on which we're allegedly sitting, because after all, the Godel result is itself something that belongs to meta theory. But even from the standpoint of set theory, we have no trouble saying that the standard model of arithmetic is countable. So it's hard to believe that there are significant epistemic consequences that flow from the Leeuwenhoek-Scullum theorems. If you can't get there by Godel, you're not going to get there by this result either. And I will pause at this point and give people a chance to say something again. If there's anything you want to say. Okay, onwards. So despite what I said earlier, it might be thought that there are results that show that there are mathematically interesting limitations to the Peano axioms. In particular, it might be thought that a family of meta results about the branch of mathematics known as Ramsey theory shows that this is so. So there's Ramsey, one of my heroes on the right. Perhaps we can use this family of meta results to bolster the idea that first order meta theorems do have significant consequences for our knowledge of arithmetic. So here's a question from Ramsey theory. How big does a party have to be for it to be true that there are 3 people at the party who satisfy the following condition? Either prior to the party they were mutual acquaintances, or prior to the party they'd never met one another. That's a question in Ramsey theory, the theory of the size that structures must have in order for their substructures to satisfy specified conditions. And I hope you can see why that question fits the general account. Ramsey theory embeds Peano arithmetic, but it contains more axioms about structures and substructures and so on, and actually rather more than that, as will become clear later. So what about these pictures on the right? Well, this is, having asked the question, I should answer it, right? So the top diagram shows you, interpret the red lines as never met one another and the blue lines as being mutual acquaintances. If you've got 5 people, you can color the graph in such a way that you don't get a triangle connecting 3 of the black dots all of the same color, right? So that's an equivalent way of thinking about the problem. What it shows is if you've got 5 people, it's perfectly possible that you don't have a subset of 3 who are mutual acquaintances, and you don't have a subset of 3 who've never met one another. If you try to do this for 6, so here's an attempt on the diagram on the bottom, the hexagon, you'll see that in my example here, Anne and Brian and David are all connected by red lines. So that would be a triangle of 3 who never previously met one another. It turns out, I'm not going to try and prove it, and I'm not going to try to convince you that it's true, but you can't do for the hexagon what I was able to do for the pentagon. And so the answer to the question is 6. Now, here's the interesting thing. There are theorems in Ramsey theory that are, in some sense, purely theorems of arithmetic that can't be proven from the Peano axioms. So Paris and Harrington proved a result of this kind in 1977, but Goodstein, Jensen, Kreisel, and Paris, but the first 3 in particular, much earlier, had given related results or pointed to related results. There's a paper that Kripke published in last year, it's still last year, I think, where he talks about the history of these results and points out that probably credit here should be given to Goodstein because he had a result of this kind about 3 years after Godel published the incompleteness theorem. And there have been others who've since proved similar results also about theorems of, I should say the Goodstein result's not about Ramsey theory, but there are other people who've proved similar results in Ramsey theory. There are things like the Kanamori-McAloon theorem. Now, this might seem to be a double-edged result. On the one hand, Peano arithmetic seems to be significantly incomplete, but on the other hand, we have an independent proof of the missing theorems in Ramsey theory. Right. So it's straight off, it's not exactly clear what we should conclude from this about epistemic limitations that you might have thought you were getting out of the Godel theorem, because we have this proof that you can't prove certain things from the Peano axioms, but it turns out that we can prove it in other ways, right? And so you might wonder whether that doesn't really in the end undercut any temptation that you might have had to think that there is sort of significant limitations that attach to just having the Godel proof. Now, I'm not sure about this at all, so people who know more about this might want to jump in and correct me here. There's reason to be skeptical whether the Paris-Harrington theorem and all those other things have dramatic epistemic consequences. In particular, I think it's worth noting that plausibly it's only because the relevant claims are false in some non-standard models of arithmetic that these claims are not theorems of Peano arithmetic. Said differently, the proofs of these results in Ramsey theory rely on claims from the higher reaches of set theory that go way beyond Peano arithmetic. That's why you can't prove them. I mean, imagine that somebody said, here's this result, and you needed the axiom of choice to prove it. You couldn't prove it from the Peano axioms because the axiom of choice wasn't in there, but that's kind of not, that's not the fault of the Peano axioms. It's just that there are these other resources that mathematicians are happy to give themselves. And if you're prepared to give yourself some assumptions about high cardinals, for example, you can prove things that you can't prove without them. Right, so maybe I've jumped ahead of what to say. So given what I've said so far up to this point, I think we should be very skeptical about claims for the broad epistemic significance of the Godel theorem, or actually for the Paris-Harrington theorem, or for the Leeuwenheim-Schuller theorem. And I should say, since I didn't emphasize this at the beginning, but it was probably obvious, that's not to say that these results have no significance. They're all very important. They were very significant for foundational questions in the philosophy of mathematics. I take it that Hilbert and indeed Russell and Whitehead were not happy when they learned that they were wrong. Right, and so of course it's significant, but it's not going to do any of the kind of work that somebody like Turner might have been hoping that it would do. Okay, so let me pause again, and those people who know more about Paris-Harrington theorem and so on might want to correct what I've said.
Sorry, Grant, can you hear me?
Yeah.
Yeah, I mean, no, I was not going to talk about the Paris-Harrington theorem, but I was going to make a little remark, which I think that you will enjoy. In fact, when you made the connection between the Leeuwenheim-Schuller theorem and Godel's theorem, there is a little paragraph in Kleene's book, Introduction to Metamathematics, where he says that the Leeuwenheim-Schuller theorem is the first of the incompleteness theorems. And why does he make that remark? Well, because it shows that the notion of countability was not axiomatizable within the realm of self-theory, right? So it was a relative notion. And in a way, that's also what the Gödel's incompleteness theorem is showing you, right? So maybe this is a reference that you might want to include there in the paper.
Yeah. Right, I should say there is no paper, there's just a talk. I wasn't even planning to write this up, so, but I was interested in getting feedback on what I've been thinking about, so. But yes, of course you're right, that's very helpful. Okay, so we go on. There's one last little bit. So I'm much less sure about this bit, but I want to consider an objection. So in my discussion of our ignorance of the theorems of Peano arithmetic, I took it for granted that exponentiation is total. If n and m are numbers, then n to the m is also a number, right? My example about the Googleplex was based on that. This assumption's been contested, perhaps most famously by Ed Nelson. That's him in the picture. If we adopt Nelson's strict finitism, then there's this question that comes up. Could we claim both that our knowledge of the theorems of Peano arithmetic is not interestingly limited, and also that Gödel's theorem reveals an interesting epistemic limitation to which we are subject? Right, now this might seem like a little bit niche because there aren't lots of strict finitists out there, but I think Nelson was a very considerable figure, and I've always been interested in his work, and so it seemed like a good question to pursue. So what I think is this. Standard proofs of Gödel's incompleteness theorem rely on the assumption that exponentiation is total. The way this works is through the way that the technique of Gödel numbering is developed. So I'm imagining this is not a completely worked out case, but it illustrates it. We start by numbering the primitive symbols of the language of arithmetic. So over here on the right, I've got 1, 2, 3, 4, 5, 6, right? Just assigning numbers to left parenthesis, right parenthesis equals, I've left some out. There's got to be a semicolon and various other things, but a whole lot of symbols. And then we use prime exponentiation to code sentences in the language of arithmetic. So for example, under the coding that I've given there, 0 equals 0 gets assigned 3 to the 4th by 5 to the 3rd by 7 to the 4th. And notice that just kind of simplify things, that 3 to the a by 5 to the b by ... p to the c is going to be greater than 3 to the a plus b plus ... plus c. Even moderately complex sentences are going to be coded using expressions that officially Nelson won't say are definitely numbers. Right, I've said that he denies their numbers, but maybe that's a little bit strong. And we haven't yet considered how to code derivations, which just increases the complexity, right? So I suspect that you can't be sure, if you think about the details of the Gödel proof, that the n that kind of you're crucially relying on when you're constructing the Gödel sentence is a number at all by the lights of strict finitists, because we've got this use of exponentiation in the development of the numbers. So I suspect that you can't, if you're a strict finitist, you can't rely on the standard proof to tell you that the Gödel incompleteness theorem holds. And at this stage, I don't know of any other way of proving the Gödel incompleteness theorem that is something that bypasses going through Gödel numbering. If there was, then that might solve the problem, but otherwise it seems to me that strict finitists have no reason to accept Gödel's result. And so that's the last thing that I wanted to say. And I'd really like help with this because I'm not sure that what I've said is right, but I suspect it is.
A question about that. So first of all, I don't have a lot of knowledge about the way Godel has numbered everything, but I was wondering if we could just use these strings of exponentiation as symbols, basically, and continue, like from a strict finitist perspective, you could still possibly read the proof without thinking of them as numbers, and just think of them as just symbols, and there's, you could like define a whole calculus that explains the proof without us considering them as numbers? Would that be something?
So I'm not sure, maybe someone else can help me with that. I think that's not right. I think you have to think of them as numbers, but
So I mean, it depends on what you mean by that, but so you mean that, well, of course, all of these numbers could be constructed from a finite vocabulary, right? The vocabulary of arithmetic is finite. Here the question is more, I mean, I have to think what it would mean, honestly, to code things from a finitistic perspective, because if you are a strict finitist, you probably don't even believe that there are infinitely many formulas, right? Because you're a
that's
strict
right.
finitist. So then I'm not really even sure what it means to formulate the problem in that context. This is not something that I have looked into. But of course, I mean, let me say that this Godel coding is, of course, only one of many, many possibilities, right? You could code everything in binary, for example.
Yeah.
Right? And stuff like this. You could do some tricks.
But that one, so coding in binary won't solve the problem.
Yeah,
about
no, of course, no. I mean, I don't know what solved the problem, because the more essential problem goes down to the fact that, yeah, what does it even mean for a strict finitist? How could you possibly? I'm not sure. Yeah, I don't know. Maybe someone else knows.
I mean, like, can a strict finitist consider these things as just strings, like how in computers we just have those strings? Would that even work? Like, that's kind
Yeah,
of...
but the problem is that, these strings, they have to correspond. Like the Gödel thing is like the coding
To
of
the binary.
syntax. No. I mean, but they have to correspond to something, and the problem is that you have infinitely many symbols in the syntax, right?
Yeah.
What does the strict finitist do with that? Like, how do they represent a syntax that contains infinitely many symbols? I don't know. I don't even know what do they do with syntax. I really am not. I'm not aware of what the approach is there.
Yeah, but it makes sense now. Thanks.
So if you're a strict finitist, I mean, I've made a list of variables there, kind of x1, x2, x3, x4. If you're a finitist, you're not going to think that there's infinitely many of those in the syntax, right? Because at a certain point, these things that I'm using as the subscripts aren't numbers according to the finitist. So
yeah, but I mean, yeah, it's even worse, because it's not just the number of variables. The problem is that from those variables, you define the notion of a formula. And then I can prove to you that there are infinitely many formulas, right? Like, how do they code that? I'm not sure.
so they will think that you can't prove that there are infinitely many formulas, though.
Right? Yeah, I suppose so. Yeah, that's true.
Is it that you can't prove that you have infinite formulas, or is it that they think they don't exist?
Well, the latter is more fundamental, but if there aren't such things, then you can't prove that there are. There's got to be something that's going wrong.
Yeah,
but
actually, let me stop. Yeah, no, actually, okay. So, but if you're a strict finitist, I have no idea, because honestly, I have not looked at how they see Gödel's theorem or anything like that. But I'm just thinking off the top of my head. If you actually believe that there are only finitely many numbers or whatever, there are only finitely many whatever, that means that your model of arithmetic is finite, right? But then if your model of arithmetic is finite, sure, you can give a recursive axiomatization of that, because it's all decidable, right? You can decide what is true or not. I mean, in principle, at least,
Yeah, in principle, because in practice, it's not like Nelson thinks that there's an upper number, M, that's the big number, and the numbers stop there.
Yeah.
That's not part of the view. So, it's kind of tricky.
Well, I mean, if they're a strict finitist, they have to believe that there is some upper number. It's just that the number is too large for them to even reach it in any conceivable time or something. Like it's something like larger than than the number of atoms in the universe or whatever, whatever it is. But I suppose, I mean, if they're a strict finitist, like in the sense of like actually thinking that. That there are only finally many numbers to play around. They don't give you a figure of what the highest number is, but I mean, I suppose that this is what they mean by that, no? Like
So,
that the number is so large. Yeah.
so weirdly, well, I don't know. I mean, I have trouble understanding it, but Nelson thinks that addition and multiplication are total. It's just that exponentiation isn't. So if you can write down two things that are numbers, then their sum will be a number. But when you write down something like the formula for a Googleplex, he just thinks that that's just rubbish. You just haven't written down something that corresponds to a number. That's his view.
Yeah, because
it's very weird. But
if I can weigh in, then that means you have to break recursion, right? Because you can define exponentiation recursively from.
You would have thought so.
Yeah.
You would have thought so. Yeah.
Exactly.
Yeah.
I mean, when
Yep.
you try to take a really large number to a power of a really large number on your phone or some kind of calculator, it'll give you infinity anyway. So maybe he's basing it on like the computability of exponentiation rather than the ability to compute it.
That could be. I mean, if that's what they mean, then this is more along the lines of computational mathematics or something like this, not sort of constructive mathematics. But I think that they mean something more hardcore than that.
Certainly Ed Nelson meant something more than that. He was not thinking about the limitations of computers. He was just thinking that in a way that I don't fully understand.
Me neither then. Because I could totally understand, like, if he was coming from a computational perspective about what's the biggest number you can compute on a computer or something like that. But I wouldn't see the difference with that and Nelson, because it's a bit far off.
Okay, so now I suppose the floor is open for questions about anything that I've talked about, now that you've seen all the bits, because you might be puzzled by some of the bits in a lot of other bits. I don't know.
Something I was just thinking about when you were talking about the Ramsey theory section is that, like, well, I don't know, for me at least as a mathematician, one of the interesting consequences of the downfall of foundations of math, well, the pseudo downfall of foundations of mathematics, is like there's now multiple research areas in pure mathematics that essentially embrace this idea. I mean, you have things like the set theorists who, like, it's like, oh well, we don't care if the continuum hypothesis is true or false in ZFC. We're just going to do set theory with it, and we're going to do set theory without it, and we get interesting independent results therein. And like this is, you know, shattered into a diverse array. And then you have like something like reverse mathematics, which looks to be like, well, like we can actually look the other way. We can look downwards and say, let's start stripping away what we have and work out, if I take away this, what do I still have? If I take away this, and you get this lovely like classification of how much mass generates how much other mass. To some extent, I think like the epistemic impact of that is less about like, oh, does it tell you something profound about the limits of knowledge in the universe, and more just like, if mathematics, widely held up as the like last bastion of foundationalism by epistemologists, if even that has moved to a world where everything is relative to something and you just work within the systems that you're given, and truth is defined via discourse in the community, that I think is an interesting epistemic, you know, it's mathematics for like it no longer existing as that exemplary.
Do you think, to what extent do you think that you could sheet that home to Godel though?
I definitely think there's like an element to which that because I mean, like, you know, the incompleteness theorem was one major moment where, like, you know, Hilbert and Russell and these people did have to like change, at least like it fundamentally shook the idea that there is one true axiom base and from which everything flows. So I mean, like, but maybe more important historically than, like, you know, as like philosophically.
Right. So because there are other things, like there's a debate about choice, and then there was, you know, the stuff about the continuum hypothesis and so on. Right, yeah. I
mean, one of the important corollaries to Gödel's result is that, like, you'll never escape this cycle, right? This is important. So it's, you know, because even with stuff like choice, I mean, some of the arguments there is just we just include it, right? And maybe there was for a long time. You could have believed there was a hope that eventually we would. Like it might take a really long time. We might have really difficult discussions about the final full axiom set in its full generality, but maybe we would eventually get there and settle on one that does satisfy everything. And then Godel's result says no. Like you can add as much as you want, and there will always then be more statements beyond. In that sense, that is quite important. Like it killed any belief that we might eventually escape this cycle. The cycle is forever.
So you can maybe enlighten me about this as well. So I think Hugh Wooden has sort of been arguing that maybe we can eventually get to a kind of fully determinate set theory, right? Where you kind of have, you get up high enough and then it just kind of forces everything at lower levels, and so you end up with fully determinate mathematics. It's not clear, sorry, a fully determinate set theory, right, without the choice points of various kinds. I suppose then there's still a question about the extent to which set theory is, where you think you've got to think that set theory is foundations for all the rest of mathematics or not. This is in terms of the kind of cycling thing that you're talking about.
I mean, it's been a little while, but I'm fairly confident that the corollary to Gödel's theorem is that in any system sufficiently rich enough to express arithmetic, you can write down the Gödel sentence, and this will be a statement of the system. So there is no escaping.
Right.
Like you can't jump other than just saying everything is true, right? You can jump to contradiction, and that's fine. Like, but then that's inconsistent, right? You need the consistency, right? In any consistent theory that encodes arithmetic, there are always stuff it doesn't decide. So you can't escape. You can add theorems, you can add axioms forever, and you'll be forever lost.
But that's okay, because the Gödel result only talks about recursive axiomatization. So you might just think there's so much of mathematics that you can't recursively axiomatize it. It's not.
I guess maybe you could make the claim that eventually all interesting mathematics would be within our reach. But I mean, I don't know. That's like, well, I guess that's like a discourse level question, right? It's like
right. So it depends what you mean by within our reach too, because there was that earlier discussion that I gave about simply the obvious sort of straightforward consequences of the Peano axioms that we can't that we in some sense we can't grasp them. Now you might suspect that in the language of mathematics, there's going to be quite a lot of stuff that sort of escapes us for those kinds of reasons, because the results, even on the neatest way that we could find to write them down, they're just too long for us to understand them, right? I mean, I don't see why it isn't sort of reasonably intuitive that, you know, there's lots of mathematics that unless we find ways to increase our cognitive powers, there's lots of stuff that's just beyond at the moment that we'll never get to. And then perhaps there's more, right? Way beyond.
By the way, Grant, if I may interject, just going back to the strict finitism thing, because I was Googling real quick here to get a picture. And apparently, I mean, what I found online is that, well, I mean, there are very different approaches, but I think that what seems to be the most standard is that they do think, this is what I had in my mind somehow, that they do think that at some point, one number is a successor of itself. Right? There is a very large number that is a successor of itself, because of course they change the axioms a little bit, they tweak it, they make it such that the successor operation is not necessarily injective in the way that you would expect it, or like, you know, it's not an injective function, but that's the trick, no, that at some point there is some successor of itself. And I also wanted to say, I mean, this is related to the discussion that you were just having with James. Do you know there is a paper by Chaim Geifman, that I think that you will enjoy. And I think that this talk, you should turn it into a paper because I find it interesting. Why not? Right? So I'm going to copy the paper here on the chat because I think that you will find it interesting. And this is very much about this topic. No, the title is What Gödel's Incompleteness Result Does and Does Not Show.
Right.
And he argues, essentially that, yeah, of course, it could very well be that indeed there is a set of all mathematical statements that are out there, right? Of course, I mean, and there is, it's just that we will never be able to fully grasp it. In the sense of grasp it by means of, you know, finding a recursive axiomatization and all of that, that's just Gödel's theorem, no? But there are other ways of, and for example, he uses this to conclude a thesis on the theory of mind, no? And he kind of agrees with Davidson, no? That the mind is a kind of mysterious thing in the sense that, yeah, sure, there is a way that it works. It's just that we cannot put it in an algorithm, right? You cannot locate the algorithm, even though it might exist somehow, no? It's just beyond your grasp because it cannot be put in this kind of recursive fashion. So I think that this paper is very good. And the author is, of course, a glory of mathematical logic, that guy Geifman. So it's really worth reading, although now he's a philosopher, but well, he used to be a very important logician. So yeah, just those two little comments.
Okay, I'm just going to copy it down because I know if I don't, once we close, I will lose what's in the chat. So thanks for the reference. I will have a look at that.
All right, guys, is there any more comments, questions, remarks for Graham?
I'm wondering, Graham, do you have any reflections on Gödel's own conviction that the truths of mathematics are, loosely speaking, out there, and that they're accessible, at least to those of us who have the right kinds of noetic rays to reach them?
I guess that's not my, yeah, I guess that's not my favorite philosophy of mathematics is what I say. But it's not because I have a definite opinion, but I'm not particularly attracted to the noetic rays. No.
Right. The real question is whether you see any way of connecting this is almost a question of flavor or inclination, or the kinds of personality issues that William James talks about in Varieties of Religious Experience. The people who want to enlist these technical theorems for certain kinds of epistemological purposes that Godel would have been, I think, deeply out of sympathy with, and Gödel's own attitude toward them. That's pretty vague.
Yeah. So I don't know that Godel and Dennis Turner would have got on. So.
Well, they would have agreed on their theism, but they
Yeah,
might
they
might have disagreed profoundly about how you get there.
Yeah, and I think that's true. Yeah.
Yeah.
So no, I don't think I have anything particularly interesting to say in response to that question.
Yeah. Okay. Fair enough. Well, I was struck. I'll make a comment since no one else is weighing in. It's striking how these very pedestrian considerations about our cognitive limitations already seem to make any points that might come out of the incompleteness theorems for the generality of our epistemology of mathematics. There's still, as has been said already today, very important in the history of the foundationalist programs. But there's something very deflationary about your starting point of saying, look, just think about some really big sum that you can't do, and if you think you can do that sum, think about some much bigger sum that you can't do. Doesn't that already make whatever epistemic point is to be made? It's striking how pedestrian that is.
Yeah, so it seemed obvious to me, right? It does seem like a really pedestrian point, but when you look back at the history, almost from the time that Godel produced his paper, there are lots and lots of people trying to inflate it into something much more. Lots of theorists on both sides of the kind of analytic continental divide, right? You can find people on both sides doing this, and that just seems really puzzling to me.
I mean, oh, sorry, Lloyd wants. I'll let.
Lloyd.
Okay, thanks. I just wanted to make two comments about expository matters. One of them is in the Paris-Harrington slide with various formulations, and now I don't know what the details of these so-called genuinely mathematical examples of incompleteness are, but it's probably going to be necessary to point out that the apparently second-order nature of the formulations that feature on your slide is not essential to the point, because we are talking about first-order arithmetic, whereas those formulations talked about there being various sets of natural numbers that do such and such.
Yeah, yeah.
And the second point is when you sketched the beginning of an axiomatization of basically Peano's axioms, but you stopped. You didn't include addition and so on, multiplication, and you said, well, we could define up addition and multiplication and so on. That phrase, define up, made me think of define in the sense of theory of definition and theory of definability. And recursive definitions are nothing to do with that, because, I mean, you get what I'm saying. You could, the Turner paper even mentions that if you have the restriction of the Peano axioms to first order version to goes as far as addition, which doesn't include multiplication, then that is actually a decidable theory.
Yeah, yeah.
So there's no sense in which multiplication is definable in terms of addition and successor, even though the so-called recursive definition involves two axioms featuring only those as non-logical symbols aside from multiplication. The point being that those recursive definitions do not suffice as a proper definition is supposed to allow you to eliminate the symbol being defined by using the definiens. So that's just expository things that I found slightly maybe worth more attention than you gave them in passing.
So it was exactly, partly for this reason that I'm not thinking of publishing, because publishing the paper, why I was just, because I mean, I agree with what you just said. And I mean, in my kind of bumbling way, I've been worrying about it, but I think that maybe it would be better to actually have explicit axioms for multiplication and addition and include those. Would that be the best way
Absolutely.
to respond to what you said.
Uh,
Then I would have to choose some, and it would have made the exposition more tedious, but it would have also made it more accurate. So that was
Yes,
just
and
bad,
apparently,
bad on my part. But that's this is a kind of recurring worry I have about a lot of the things I talked about, that there are lots of technical issues just below the surface.
right. And apparently, although intuitively we think of the sequence, successor function, addition, multiplication, exponentiation, tetration, and so on, as just a different quantitative stages. In fact, there is a qualitative difference in that Gödel's argument actually shows you can define exponentiation explicitly, I think, in terms of the once you've got addition and multiplication, the successor function. So there's actually an abrupt difference there, as well as this abrupt difference that Pressburger arithmetic with any addition is in a completely different category as far as these would-be epistemological issues are concerned. Yeah.
Thanks, Lloyd.
I was going to ask you about the epistemological dimension of all of this, because it's very easy to get buried in the consequences of axiomatizations, theories, and so on. But what is the nature of the epistemological enterprise? What are we doing in order to further knowledge, belief, or whatever? And one way of looking at what's happened in mathematics in the last bit more than a century has been to convince ourselves we know a hell of a lot more than we might have thought we could cope with. So one way of coping with vast arrays of numbers is to try and do finite axiomatizations. So we enter into that enterprise, and once we enter into that enterprise, then we have to satisfy ourselves that the enterprise isn't a dud. And what we seem to have discovered since Frege and set theory is that there seems to be a limit to the epistemic enterprise. Well, that's, in some ways, that should have been obvious right from the beginning, because for any given human agent, there has to be some sort of limit. And I think the enterprise, and don't forget that mathematics is extraordinarily young, far younger than language, far, far younger than language. It's, if we go back to Euclid, that's not very far. And nobody has mentioned geometry. We're all talking about numbers. And we're not talking about algebra. We're talking about numbers. So geometry, no mention. Algebra, no mention. Numbers is it. And I think that's a really interesting part of the epistemic enterprise. What are we trying to do about numbers that makes us set up these axiomatizations and look at how far they go? So if we've got a finite axiomatization of first order logic and throw in the Robinson arithmetic, how far does that take us? Well, for the average person working in the area, or better still, beginning in the area, it's quite difficult to get to understand and to know what's going on. Once they do, then it's very easy to be caught up in the game of consequences. And I'm just wondering whether we have the epistemic ability to know about the consequences. I mean, we write it all out and we talk about it, but what do we know about the continuum hypothesis? I mean, that's just to start off with.
Okay, so one of the questions, so there's a bunch of different questions that you asked. One of them was about why numbers. That I think is just because the Godel result applies to anything that embeds arithmetic. And I take it that, for example, algebra embeds arithmetic in the, because you have all of this stuff simplifying algebraic expressions that's got numbers in it as well as variables, and geometry embeds arithmetic as well. In fact, it'll probably embed the reals. And maybe there are kind of super abstract ways of thinking about geometry in which, well, but I doubt it, right? So there's a reason why numbers in this context, because the Godel result is so general. Does that address that particular worry that you were raising?
What you just said about geometry is really interesting, that maybe geometry is about reals. It is certainly about intervals. And immediately you start talking about intervals, you run into a kind of blank wall. And we seem to be nailed down to sets of discrete objects. And we really seem to lose our way very quickly when we start talking about intervals and things that look anything like real. Although we don't usually take people out and drown them for talking about reals. Not anymore anyway. So it still raises the question, we're still looking at the old question, what are numbers and how do we know them? And I think we've been looking at consequences in a way that really raise questions about the perspective that we've had on numbers. Somehow or other, it leads us into all sorts of internal difficulties, which we hope will be solved one day. But at the moment, you don't have to go very far to run into puzzles. I mean, I don't mean the kinds of puzzles that occur in naive set theory, unqualified naive set theory. I'm thinking of puzzles like, what is the relationship between the rationals and the reals? And I mean, that was the first thing that really puzzled me when I was doing transfinite set theory and recursion. But recursion, it seems to me, is an attempt to grapple with a whole lot more than just an infinite list of numbers, a non-ending list of something. It's an attempt to pull it all down into something comprehensible, even though we don't know all the consequences. I mean, so much for epistemic logic and the distribution and closure principles in it. It just does not work. And it's interesting that when you talk to mathematicians about these things, they're all interested in theorems and meta-theorems and so on, And when you talk to them about arguments which have contingent premises and contingent conclusions, they switch off. They switch off. That can all be dealt with in 20 minutes, they think. So when we look at first order logic and first order arithmetic, are we getting sidetracked into something that's fascinating, but sidetracks us from the main enterprise? And the main enterprise is contingency, not theorems. Anyway, toss that in for people to boo out and so on. Ha ha. But what struck me about the paper was that there wasn't really a great deal about epistemology. Sorry, Graham.
So again, there's lots that I might respond to there. I mean, one thing that is interesting, and I'm not particularly a philosopher of mathematics, but one thing that does seem to have changed in the attitudes of mathematicians is how much more kind of empirical stuff, sort of use of computers to find results, rather than worrying about having explicit derivations. I think that this is just my experience talking to mathematicians at Monash. That's something that's changed quite a bit in the last 30 or 40 years. But it's still true that mathematicians are very concerned to prove things, right? Logical consequence is one of the main games.
Yeah,
right?
definitely.
Yeah.
And it's one of the trickiest parts of the game. I think that's why we've got this enormous blossoming of non-classical logic, because logical consequence is so tricky. And if you combine it with epistemology, it really gets very, very tricky.
So I mean, to pick up on something that I think it was James said before, I mean, about the way in which mathematicians have been thinking about what if we didn't have this, what could we get? Logicians have been playing that game for a long time too, and the two things intersect. So, you know, you can look at what you can do with a kind of paraconsistent mathematics, for example, where you don't allow yourself some of the rules that you're going to have when you go classical and see what you can prove, right? That's also a feature of the landscape now that wasn't there 100 years ago.
Yes. Well, maybe that's because of the epistemology. There are certain features of the classical approach which seem to be epistemologically unacceptable. And going paraconsistent is an attempt, I think, to clean up the epistemology. Going even further to dialethic with Chris Mortenson's inconsistent mathematics is really interesting, but that's following out the consequences of the first couple of epistemological steps. And it's beginning to, in that case, when you talk to Chris Mortenson, he talks about how important his inconsistent maths is for robotics. And when he started talking about that the first time I heard him, I found it very surprising, since I was in the automated reasoning project and places doing a lot of AI stuff. And I'm still not sure what goes on when someone says that they know that 1 + 1 = 2. I'm not quite sure what's going on when they say that. Other than I used to sing it in grade 1 at primary school.
Wait, sorry, just to jump in, I mean, like, to some extent, a lot of this, I think it's really, like I mentioned, like having a robust philosophy of mathematics is gonna quite robustly affect like how you feel about these things. But this is exactly one reason. I mean, like there's one strand of idea in philosophy of mathematics that looks to like mathematics much more as a, you know, as a community of people throughout history, and then to some extent the foundation of mathematics is the education in mathematics you receive as a child. Like that is what mathematics is, and then all of the foundations we've developed thus since are just retroactively tidying up what we've, you know, learned in our primary school classroom from Mrs. Smith or whatever. But so I would, as at least someone who finds the philosophy of mathematics very interesting, like I think trying to tease out like what impactful or seminal results in mathematics are going to teach you about, or what wider epistemic considerations they're going to have, it's going to be intimately bound up in how you think about mathematics at all. I'm not sure you can necessarily get away from that.
Well, children like singing things, and they you sing all the way up to the 12 times table and so on. Take a different look at that. When we were doing computing at the Automatic Reasoning Project and we're using Prolog, what we found, Prolog is in some sense recursive. And what we found is that we could really speed up calculations by having a huge number of basis clauses in our Prolog programs. Theorems in a list of theorems were provable in the twinkling of an eye in dead slow old Prolog. Think about what's going on in primary school when kids sing those addition and multiplication tables. Then what you've got is a huge basis clause. Now, someone comes along and says, oh, well, we should teach them set theory. And I'm thinking to myself, this is a total confusion of theory and pedagogy. Total confusion. And if you think of what those simple arithmetical stuff is taught, and then think of that as the basis for the recursion clauses that follow on from it, that means that these young mathematicians can do very quick calculations, but that doesn't make us happy as logicians. We want to reduce it right down to 0 is a number. And I don't think in any of the songs that I sang in primary school, I multiplied anything by 0. That's interesting. And yet here we want just one number, and it's 0. That's the starting point. Not even 1. I think it used to be 1 at one stage. And we want to build the whole of arithmetic or whole number arithmetic on 0. And I think that's our epistemological attempt to shrink the whole lot down into a very simple form, but the form might be too simple. It might be too simple epistemologically. We would be better to have a more complex starting point for our epistemology and have a whole lot more in the recursive clauses. But then what I'm suggesting is a little bit heretical, to say the least. I think we've got to wrestle with the epistemology of what's going on here. And when we say, I know that 1 + 1 = 2, how do you know that? To put it in an Austinian fashion, it's not a justified true belief. It's an answer to a question. How do you know that? Then you ask, well, what's the way of saying how people do things, well, you tell a narrative, you give a story. And the story that we've been giving is a story about axioms and rules of inference. I doubt very much if that is as helpful as we think. But it's an open question, isn't it?
So I think I want to agree with something that James said before. I mean, if you really want to do philosophy of mathematics, you should look at what mathematicians are doing now, study what they're doing, and use that as the basis rather than trying to start from some philosophical assumptions about what they ought to be doing or what you imagine that they're doing or whatever. And I think that it was rarely the case that mathematicians proceeded by, first of all, dreaming up axioms and then churning out consequences from their axioms. I think that just, I mean, maybe it sort of happens when you're writing a textbook. So, you know, if you go and look at, I don't know, Burgess and McLean or some other textbook like that, they will start with some definitions and some axioms and start proving theorems. But that's pedagogical and only has to do really with pedagogy. It's not what mathematicians really are doing when they're at the cutting edge developing new stuff. So anyway, that's just my thought.
Well, that's part of the puzzle, isn't it? They seem to know what they're doing. Well, they certainly think they do. And they're not doing a lot of the stuff that we've been talking about. So what's going on epistemologically there?
So, well, one of the things that's going on is that philosophers are very, and it doesn't just happen in philosophy of mathematics, but they are inclined to make assumptions that they think must be right, and then they get things wrong. And so you get kind of misguided views about what mathematicians actually do, right? This is quite common in other areas, so I don't see why it shouldn't happen in philosophy of mathematics too, or why it didn't in the past. I'm imagining that lots of people who work in philosophy of maths these days actually get out there and collaborate with mathematicians, talk to mathematicians.
I just want to add something about the concept of axiomatization in math. And I think, like, historically speaking, geometry started by having a set of rules about things that seem to be obvious. So if you were to consider geometry as one of the cornerstones in the history of maths, you would have to consider that it was intuitive from the very beginning to start with axioms rather than something that you would do for writing a book. That makes sense.
So I guess we don't know where Euclid started, though.
Yeah, but like,
What his practice was, how he came to write the book.
yeah.
But given the kind of worries about the parallels postulate, I suspect that he didn't start by thinking, yep, those are the truths, now I'm going to start deriving things from them. It was, you know, I need these things and maybe I need that one too.
Yeah.
Well, it was one way of looking at Greek geometry is to see it as the outcome of the development of navigation skills. It was a naval empire, and they started to work out ways of orienting themselves in the Mediterranean and working off points. And there's the calculation machine that has been discovered, which helped them do those things. And so you've got this this chap sitting around watching what they're doing and thinking, what was he thinking? Can I kind of put this all together neatly so that they've got an even more reliable basis for what they're doing as they sail their ships around the Mediterranean? I think there's a lot of evidence to suggest that Euclid was working in that ethos of a naval civilization. And it's more interesting for them. Geometry is far more interesting for sailors than is arithmetic. And the
So-
same. Mm.
So I've read some very old histories of mathematics. I think Heath has one of the standard ones. And the suggestion there is that actually the first interest in geometry was probably dividing up land amongst heirs, working out how to do that, straightforward way. And that will be long before, I think, the navigational stuff. But that's just a guess, and it's relying on my memory of reading stuff by historians of mathematics who probably no longer read anymore either. So,
Oh, well, there's the building basis too.
yeah, I mean, there's a bunch of things.
So out of this emerges Euclid. It's not as if
Well, I'm not sure what's the date for Euclid.
it's only about 400, isn't it?
So 400 BC, because the Antikythera mechanism's much later than that. It's either 100 AD or 100 BC. It's somewhere in that period.
I just
Anyhow,
googled
so-
it. It
so-
was like 300 BC. Thanks.
What's that?
I'm just googling it.
Really? I thought it was later than that.
Yeah. Yeah, I don't know.
So the shipwreck, I thought the shipwreck was, for some reason, I thought the shipwreck was much later than that. Oh, well, Google will know, I guess. So there's a bit of epistemology for you.
Yes.
Sorry, guys, I think Peter had a question. Peter Ellerton. Peter, please go ahead.
No, I'm sorry, Guillaume. I had my hand up briefly, but I put it back down again. All questions were answered to my complete satisfaction. Thank you.
All right, good. Excellent. So I think that with that, maybe, unless there is some final questions, maybe we have tortured Graham long enough. It's already, 40 minutes past the time that he was supposed to to give his talk. So is there any final question, remark, comment?
Actually just want to ask Rodney.
Go
the
ahead. No,
question.
yeah, please.
Yeah, it's not just a question about the guy who was doing inconsistent maths and robotics. What was his name? Rodney, you mentioned someone.
Chris Mortensen.
Chris. Okay. Cool. Thank you.
Excellent. So then sometimes Chris comes to the seminar. No, so Paul is in the same university as Chris, Paul Oppenheimer. All right, guys. So then with that, let's thank Graham once more for a very stimulating talk. And I think it should become a paper, in my opinion, with Lloyd's input, I can, Lloyd can look at it, he can make the actions precise for you and so on, but I think it would be very worthwhile. Excellent. Then with that, thank you so much, Graham, and I will see you all soon again next year.
Thanks everyone for the questions and discussion. Thank you.
Hopefully it was not too bad, Graham. Hopefully it was useful.
Oh no, it's very useful. And I don't know, maybe I have to find a co-author or something. I don't know. We'll see.
You have Lloyd right here, next to you at Monash. So. Okay, see you guys. Thank you for everything.
Bye.